And so we're interested in motion of vortex filaments in the Euler equation. And we saw that if I take a general curve in R3, a nice smooth curve, then I can sort of formally compute using the Beer-Savart law the law of motion. So the filaments evolve by the equation d tau gamma is, let me use subscripts. So gamma sub tau is gamma s plus gamma ss. And so here I've done a kind of rescaling in time. So maybe we said tau was something like log epsilon over 4 pi t. So if we look on a faster time scale, the same faster time scale we saw when we looked at vortex rings, then we see this law of motion, and here gamma s is an arc length parameterization. Okay, and soon I'm going to forget to write tau, and I'll call it t here. So we'll forget about the time rescaling. Okay, and so I started to look at probably, and so the goal is to understand a bit better, if possible, and so this is still a conjecture. You can, if you like, you can call this an open problem that's more than 100 years old. But the goal is to understand a bit better at least the vortex filaments in Euler, all by this law of motion. So I want to understand better this hypothetical, this conjecture, see more evidence for it. So the evidence we saw last time was not very convincing, in my opinion. And so that will involve first getting a better understanding of the conjectural limiting equation, the one that describes this thing here. And so we started that last time. We saw, for example, so this is called the binormal. It has a bunch of names, but the name I'll give it is the binormal curvature law. And we saw, for example, there's a transform that essentially converts the binormal curvature flow into the nonlinear Schrodinger equation, a cubic nonlinear Schrodinger equation. That's kind of interesting. We won't use it much. Actually, there's another transform. I should have mentioned this, that converts the binormal flow into the Schrodinger map problem. If I say, let's say T is gamma sub S, then and okay, I'm already confusing T and tau with the time variable. So let's go back to calling this T for time variable. So if I let T be the unit tangent vector, then just by differentiating this equation with respect to T nu is this. Okay, and so if I let T be the unit tangent vector, then just by differentiating this equation with respect to S, I'll find that I'll get this equation. Now T is a unit vector. So here I have a map from the real line into the unit sphere, a set of vectors of length 1 and R3. And this is the simplest, this is what's called the Schrodinger map equation. And so these three equations are all related. I don't think I'll use this very much either. We saw that. We saw some conserved quantities. So so the time derivative of the arc length vanishes pointwise, and then I was computing at the end of class last time. This, and so that was gamma ss dot gamma ss t, which is gamma ss the dot product with okay, and so if I differentiate once, then I'll have the gamma ss cross gamma ss that vanishes, and I'll have a term where I do that. And then so what I want to do now is integrate Well, okay, I'll read in your parts. The integral of this thing. And I can bring this derivative over to here, because we're using a minus sign, and then I can see that this vanishes because, of course, the third derivative of gamma is orthogonal to this thing, which is a cross product of the third derivative with something else. Okay, and so this quantity, its time derivative doesn't vanish pointwise, but it's a conserved quantity. Its integral is conserved, and this, of course, is the L2 norm of the curvature. So that's interesting. In fact, because of this correspondence, we said that this equation is cubic and less than one dimension. Is an integral equation, has an infinite number of conserved quantities. And so, in fact, that implies there are infinite number of conserved quantities for this also. But these are maybe the most interesting ones. What I want to do next is to look at, well, there are actually a few more conservation laws. And so here's the one I really am most interested in. Okay, so the plan now is to, again, we're discussing basic properties of the binormal curvature flow to develop understanding that will eventually help us go back and understand this conjecture about Euler. So another conservation law. Or say a family of conservation laws. So let me do the following thing. Let me look at, let me take a phi C infinity R3 to R3. Okay, let me remark also, this equation makes sense. So this is an equation where S, gamma is a function of two variables. There's an S variable where I think it was arc length and T variable, I think it was time. S can belong to either, it can be either periodic, it can belong to, so S can be a map from essentially a circle, or else it can be non-compact. It can be so the domain of this can be either, say, S1 cross time or R cross time. And so I'll usually think of it as being S1 cross time. I'll imagine that gamma is, that the arc length domain is compact, it's a closed loop. But that's not essential for everything we do. But it'll help now, for example. Okay, so let's take a smooth vector field, and let me compute. So if I have a smooth vector field, I can integrate it around the curve gamma. So let's write this as phi of gamma dot. Okay, so this is the natural way of letting a curve act on a vector field. So what I mean here, this is shorthand for phi of gamma of S T dot gamma, so S of S T D S, and I integrate, if gamma is a function, I can think of it as being a function, if the curve has length L, then I can parameterize it by an interval of length L. Okay, so that's what this means. And I'll use the abbreviations typically. Okay, and then it's convenient to do this combination in indices. And so let me write I here and I here. And I'm summing implicitly for I goes from 1 up to 3. I'm in 3 dimensions. Okay, and so let's compute this. And eventually I want to both derive a general identity, and then I can find vector fields phi for which this integral is conserved, keeping this theme of conservation laws for now. Okay, and so, when I differentiate this, the derivative, so phi is a function of the space variables only, but this depends, so I can have a phi I x j gamma, and then the jth component of gamma will be differential with respect to time, and that's multiplied by gamma I sub s, or else the derivative can hit here. And because I'm an analyst, I have only one thing to do, I integrate by parts there. So the first term stays the same. And then I can integrate by parts in the S variable. Yes, and so I differentiate this with respect to S. When I do that, I'll have a gamma X. I use a chain rule, and I'll get a gamma J X S. And so let me see, I can then rewrite this as this phi ixj evaluated along the curve gamma times gamma jt gamma. I've done something wrong here. Oh, that's S. Gamma jt gamma is minus gamma it gamma js. And if I look at this, I mean, for example, let's look at the terms where I is 2 and j is 3. Then what I'll have here is, you know, gamma 2s gamma 3t minus gamma 3s gamma 2t. That's a piece of the cross product of gamma s with gamma t. And then I'll have and then when I is 3 and j is 2, I'll have the same terms here with the opposite sign. And so if you think about it, what we'll get is something involving the cross product or the curl phi, say the kth component, times the gamma t cross gamma s, the kth component ds. Let me see. So there's a sign here, and shall we try to get it right? So the sign is, if I have say a 2 here and a 3 there, so I would have well, let me just look it up. I believe this is the right sign. So let me just appeal to memory, and I'll fix it later on if I'm wrong. Okay, and so now, so far I haven't used the equation. Now I'm going to use the equation, and so what I can do is I can just take the cross product. Well, let's write this as somehow I'd like it in the other direction better. Okay, and so I can take the cross product of both sides with gamma sub s. And on the right hand, and so then I'll get this on the left hand side. On the right hand side, remember that I think we saw this lesson, because this is a unit vector, because of the parameterization, the second derivative is orthogonal to the first derivative. And so here I have the cross product of some vector gamma ss with a unit vector is orthogonal to it. And so every time I do that, I just rotate by 90 degrees. And if I do it twice, if I again take the cross product with gamma sub s, I rotate by 90 degrees twice. And so this is, using the equation, this is equal to minus gamma ss. Okay, and so so let's replace that. And then I can get rid of the index notation. I have a gamma ss, and I think the minus signs have canceled. Okay, good. And again, this is evaluated along the curve gamma. Okay, and because I'm an analyst, well, I'm going to integrate by parts again. And so here I'll get, well, maybe I need my indices, the curl of phi, the kth component, and I'll have an x sub j, and then I'll have a gamma ks from here, and then a gamma js from differentiating this thing with respect to s. And then I get a minus sign. Okay, and let me write this as, I'm going to erase the equation. So I'll write this, I'll use the shorthand. This is the gradient of the curl of phi, Hilbert-Schmidt inner product with gamma s tensor gamma s. And so this is a 3 by 3 matrix whose JK component is this. And this is just, this is really I take the curl and I. Okay, so this is a Fourier matrix. And I have a minus sign. Okay, so that's, if I want to, I can rewrite it. So I'll sometimes write well, okay, what is this? So note gamma s is the unit tangent along the curve. And this is always evaluated along the curve gamma. And so what do? I take this funny 3x3 matrix built out of the second derivative of the vector field phi. And this is exactly the projection matrix corresponding to projection onto the tangent line, right? If I take a unit vector and I form this tangent product with itself, that's exactly what that is. And so if I want to, I could write this as, say, T tensor T. That's more suggestive. Or it's also useful to write this as tangent is okay, so here, what have I done? So this minus T tensor T is what we see up here. I've added the identity matrix. And so the point is that this is the curl of greater than curl of phi. This is this thing, curl of k x j times delta j k, something over j and k, and this is 0 pointwise. One can check by looking at this. This matrix is anti-symmetric. This matrix is trace free, so I can add on the identity. This is the projection out of the tangent space. This is the projection out of the normal space, right? And so. So remember, capital gamma is the name we give to the image of the curve, to the curve parameterized by the map little gamma. Somehow this representation is more convenient when we want to relate the binormal curvature flow to the Euler equation. Okay, anyways, we have this, or this. And so, so we can see right away there's some conserved quantities. So I can see, for example, if I'm interested in conservation laws, well, for sure, if this matrix is always 0, so if 0, okay, obvious, or anti-symmetric. Right, so here I have, when we wrote it in terms of indices, you could see that it would vanish on anti-symmetric things. And so the ij component here and the ji component are both multiplied by gamma I gamma j. Gamma I sub s gamma j sub s. Okay, and so anti-symmetric, and so of course, so for example, phi of x is linear. Let's see, what do I want? Say phi of x is, let's say, here's the interesting one. And so then the derivative of, and so phi of gamma times gamma sub s would be, gamma 1 times gamma 2, let's give them superscripts, minus gamma 2 times gamma 1 sub s. We could also write this as the, this is like the integral of, if I want this is the integral over gamma of the differential form, I'm just writing the same thing in different notation of x1 dx2 minus x2 dx1. Let's put half here for fun. So this is a conserved quantity. What is this geometrically? And so I have this curve in R3. When I look at this integral, I'm looking only at the first components, gamma 1 and gamma 2. And so this is like projecting the curve onto the xy plane. And then if I remember my vector calculus, this is just the, if you like, it's a signed area enclosed by the curve. So this is the signed area enclosed by the projection of gamma onto the xy plane. In other words, I have this curve in R3. I project it down here and I get a curve in the plane. And well, let me draw a picture of what I mean by signed area. So if this is the projection, then it goes around in a certain direction. Then, for example, this region is circled, say, twice in a. So I'm imagining the arrows here indicate how I traverse the image curve as I go around the source curve counterclockwise. And so this area, this region is circled twice in an orientation preserving sense. This is circled once in orientation preserving sense. This is here, this is, I have orientation reversing. And so the signed area would be 2 times this area plus 1 times this area minus 1 times that area. That's what just the ordinary thing you get from the source there. Okay, that's a conserved quantity for the flow. And so for every, and so I could have chosen x, I could have done the same thing with x2 and x3 or x1, x3, or indeed with any unit vector. And so what this says is, for this binormal curvature flow, for this geometric evolution equation, a conserved quantity is the following. I take any unit vector, I project the curve onto the plane orthogonal with that unit vector, and I look at the signed area enclosed by that thing. And that's a conserved quantity. That's conserved by the flow. And okay, we saw the arc length is conserved. This tells us right away why the why circles are stable under the flow, because circles are characterized by the fact that a circle minimizes arc length with a constraint on the enclosed. So if I take a circle who's parallel to the xy plane, it's this curve in R3 that's parallel to the xy plane. Well, it minimizes arc length with this constraint on the projected area. And so if you think about it, any curve who has the same projected area and the same arc length has got to be a circle parallel to the xy plane. And so once we know these conserved quantities, we can see without doing any computation that if I have an initial data who's circular, then it'll remain circular. And the only thing to check is how does the circle move around, which we've done. Okay, that's one conserved quantity. Another one, for example, is and okay, if my curve were non-compact, if my curve were the real line R, then I would have trouble with. I would have to worry about integration, but I integrate by parts more than once, so I'd have to worry about decay at infinity or stuff like that. But here I don't have that. I'm integrating over a closed curve. I can integrate the parts as much as I want to, and so I can take phi who doesn't vanish anywhere. I don't need vanishing conditions on phi for as long as the curve is coming out. Okay, what else? If you do this, then I think that you'll see that the gradient of the curl is an anti-symmetric matrix, I believe. Let's not bother with the computation. But the, well, yeah, so the curl of will be D2. So I'll have maybe a x2 and a minus x1 and 0. And so the gradient of this is anti-symmetric. Okay, and so this will give rise to another conserved quantity. And so then factor of a half here. Then the associated conserved quantity is well, it would be, say, if I write it, if I write it in terms of, well, if I think in terms of polar coordinates, this would be, if I have an r and a z and a theta, this would be like r squared. So in terms of polar coordinates and differential forms. So we saw that in the earlier case, I could write this in terms of vector calculus, or I could translate it in differential forms. In terms of differential forms, just the integral over gamma of r squared dz, and I think I put a factor of a half here. So what does this mean? Okay, this is something like, this also has a geometric interpretation, which is, let me just say in words. Okay, so if gamma is the boundary of some S, then Stokes theorem, this is R d R z integral over S. And so if I imagine I have some, I can't really draw very well, but say I have okay, imagine for concreteness I have a torus sitting in R3, so a surface of rotation around the z-axis, and I have a curve who kind of routes around this once. Then what I'm doing when I compute this integral is I'm roughly speaking, I'm projecting this into the RZ half plane, and then I'm computing the volume enclosed. I mean, I'm computing the volume of the torus, the volume sort of circled by this thing, by looking at the projection in the RZ half plane. And so this has something to do with the sort of the rotational flux enclosed by the vortex tube, if you like. It has a geometric meaning. I'm not sure this has any use. Who knows? Okay, so these are more conservation laws. And so here's the interest in this. Okay, so what I want to do is I'd like to view this last conservation law, or this identity really, involving the way that the curve acts on, the way that a curve evolving by the binomial curve flow acts on the assessed function. I'd like to, so we have, I'd like to view this as the key to understanding the binomial curvature flow. And the point is, so note similarity. And similarity, I mean, just for things look kind of similar to, there's a way of writing the Euler equations, the vorticity form of the Euler equations. Okay, and so for the Euler equations, one way a certain weak formulation of the vorticity equation is this, And I think we solved this at least once when we were deriving conserved quantities for Euler in 3D. And okay, well, these look kind of similar. And so the point is this exploiting this similarity, one can give a slightly more convincing argument than the sort of hand-wavy thing we've done so far. Supporting the conjectural relationship between the Euler equations and the binormal curvature flow. And the key to that will be taking this this identity as the basis. So to explore this above similarity. And so I want to know how much information is really encoded in this identity star. So we'll take this star as the basis for a definition of weak solutions, binormal curvature flow, and then we'll use that to revisit the conjecture about vortex filaments in the Euler equation. So eventually what this will lead to is a theorem that says, well, it sort of identifies the binormal curvature flow as the only, it doesn't say, well, vortex filaments evolve by this law of motion. It says, in this asymptotic regime, if there is a law of motion, it's got to be the binormal curvature flow. So it's sort of a conditional result, that sort of. But this is progress over the earlier, more hand-waving arguments. Okay, and so and so the approach here is somehow inspired by geometric measure theory, studies of things like the minimal surface equation or mean curvature flow. And so there, the idea is, well, we want to, if I have candidate for a solution of a geometric problem, well, let me reformat the geometric problem in terms of these geometric objects acting on test functions. And what one typically does is one identifies the largest class, so to speak, of objects. So we expand the class of objects, and so instead of looking at curves here, smooth curves, I'd first like to identify a bigger class of objects on which for which this makes sense. And so in other words, I'm going to introduce a weak solution. First, I have to tell you the class of objects in which I'll define these weak solutions. So okay, so toward weak solutions. Okay, and so we ask for what class of objects? For what class of gamma can I make sense of this identity? And so remember, the original equation has you know, the equation has the curvature, it has gamma, it has second orders of gamma appearing. Here I see only first orders of gamma. And so well, what do I need? I'd like, you know, I'm integrating, I always imagine I have finite arc length. And so I'm thinking, say, closed curve with finite arc length. And if I have arc length parameterization, so definitely should be okay if, so okay in the sense that I can make sense of both the left and right-hand sides of the equation if gamma is continuous for every t. And then if I want to, I can always reparameterize and gamma and okay. Well, actually, what I really mean is that if I have argument parameterization for sure, okay. Okay, but actually, I can relax it more. So one thing you see in these videos of vortex filaments, you see in water, you see, for example, two filaments who collide and interact in a complicated way. And so if I learned in this formulation, if I'm just viewing these curves as, you know, distributions who act on vector fields, well, there's no reason to insist that it be connected. I can imagine having two. Imagine having a so-called gamma, who consists of someone of two curves, and it may interact and they may collide and change topology. Or if gamma is a sum of vicious curves. Or let me actually introduce a more general class of objects, or indeed, all I really need here is I need the curve gamma to have a couple of attributes. It's got to have a position, so I know where it is, and it's got to have a tangent vector. And so let me define the biggest class of objects I can think of who have positions and tangent vectors, and that'll be or if gamma is an ordered fold. Just a measure on R3 cross S2. And so what I want is I'd like to think of these as being generalized curves in R3. Generalized, so this is oriented at one-dimensional. Barefold in R3. So this will be my most general class of objects for which I can make sense of this. Let me see. Okay, so the idea is that if I have, okay, I'll use the notation. I'll say V is one of these things. So I'll denote a generic oriented varifold by a capital V, standing for varifold. And so the idea is that if say A cross B is a subset of R3 cross S2, then the measure V A cross B should correspond to the Hausdorff one-dimensional measure of the set of points such that X is in A and C is a tangent vector. So here X is a point in R3, C is a unit vector, C is a tangent vector to the curve, the generalized. X. And Hausdorff 1 we should think of as being length. The arc length. Okay, and so this is how, and so this is kind of scare quotes. So, okay, let me give examples of oriented varifolds. And you know, if you're, you can always think of these as being basically sum of Lipschitz curves, but so examples. If gamma is Lipschitz, well, gamma Gaussian. If it's an argument parameterization, then I can. So what I'd like to do first is I'd like to know that I can associate. We can think of it as being smooth. I'd like to tell you how I can associate a smooth curve, one of these funny generalized objects. And so then I'll write V sub gamma of a set, say S. So S is a subset of R3 plus S2. This will be exactly the one-dimensional, the arc length, the Hausdorff, the one-dimensional measure of the set of points X, C. Well, of a set of S. Well, really, I mean the Lebesgue measure. Set of S in R mod L Z, such that gamma of S is in a set of points where the curve and its tangent vector lie in the set S. And so this is really just the push forward by it's the push forward of the curve of one-dimensional Lebesgue measure by the map that goes from here into this. We can call this an oriented Grassmannian if we like. It's the push forward by the map that takes a point S2. It's both its position and its tangent vector. Okay, so so anyway, this is a natural way of so I can identify it. So in other words, given a curve, I look at the corresponding curve in R3 cross S2, who is just given by this the image of this map. And I look at its arc length in R3 cross S2. Okay, or I might want to ask the sum of the arc length. Okay, so I can take so this makes sense for smooth curve. It also makes sense for Lipschitz curve, or I can take just a linear combination of these guys. When I say a measure, I mean a non-negative, a radon measure, not a sign measure. And so I can take a linear combination with non-negative coefficients if I want. I'm not allowed to have negative coefficients. And to make sure things are okay, I might as well take the sum of the arc lengths we find. I can do more complicated things as well. So anyway, this is the class of objects. I'll say this is this will be called an integral manifold. And these are what you really see in the videos on YouTube of vortex filaments in liquids, in water. You see these, maybe two curves who collide at some point. And at that point, they definitely have singularities. They're not smooth. They're Lipschitz continuous. And then as they separate, they may still have singularities. And so this is in some way the right generality to model the physical phenomena we're interested in for the binaural curve flow. Okay, and so what I would like to do is to define the notion of weak solution in this generality. Let me see what time it is. It's time to stop. Okay, so the plan is to what I'll do next is I'll define weak solutions of binomial curvature flow. And basically I'll say that a weak solution is, I'll take a family of these oriented variables parameterized by time. And I'll say if they, I can write, so for these things I can write down, the identity star makes sense in this for such objects, because all I need is positions and tangents. And so I'll say basically a weak solution is an oriented variable which satisfies this thing just written in the right language, and one or two other conditions. And then we'll study that. And these things turn out to have some interesting stability properties, which are sort of the key to understanding, to a slightly improved understanding of the hypothetical connection between the Euler equation and the binomial curvature flow. So I'll stop now. And if there are any questions, I'll stick around for a little while. And I have some old Beamer slides, which I'll post with this stuff, although there's no written record in a PDF form of this lecture. Okay. And so I guess I just also, for those of you who are still here, how do you feel about this format versus the tablet writing on using the iPad? Is the Blackboard better or worse? It's hard to get to my office at 9 in the morning, but I can. It's not impossible. So if you have any preferences about the format, this versus the one I've been using in every other lecture, then let me know. And okay. And give me a second. Okay, so and so we've reached the point in the semester at which I stop, at which I'm talking about my own work, basically. And so, for what it's worth. Okay, there's a question. Yeah, you're welcome. Okay. And you guys, Mr. Guo and Mr. Guo, and you are both in, you're in China. It's 4 in the morning or 5 in the morning or something like that. 6 in the morning. Is that correct? 你们是不是在中国? Well, I'm impressed. Forgive me, I studied Chinese a long time ago, so I'm going to entertain myself by trying to speak Chinese. 你们在中国什么地方? 哪个大学? 你们是不是研究生?
Yes, actually, I'm in Anhui Hefei.
Hefei? At 科技大学?
Yes, at the University of Science and Technology of China. Yes.
Yeah. That's Mr. Guo or Mr. Yu?
Professor, I'm Guo Dengjun.
Guo Dengjun.
Yeah. Yes. Thank you.
Oh, you're welcome. Yeah. Okay. And well, I'm impressed that your dedication at getting up early in the middle of the night. Okay. Yes, 我年轻的时候学过中文，现在很少练习。So 不知道你们能不能听懂我说的话。
Yes, of course I can understand.
Okay, good.
您说的很棒。
Very nice of you to say. So, okay, and anyway, I'm just sitting around. Any questions, anyone, or anything?
Hey, yeah, let me ask a very quick one. So how do you, when you have two, say you were talking about the reconnection or collision phenomena. So how would you define then, say in the very moment of the collision, then you have some trouble with the tangent vectors, no? And the Lipschitz continuity, or can you still give a sense to this?
Well, right. So actually, I forgot to. I'll talk about this. I'll talk about this next time. But another thing that one can do in this framework is, so if I'm talking about Lipschitz continuous curves, then I only have a tangent vector almost everywhere. But that's enough. Right. Just when I integrate, I don't care about sets of measure 0. And so I'll talk about this on Monday. But one thing we can do is one can, this allows us to study the binormal curvature flow for very, very rough initial data, such as data with initial data who has corners, a polygon. And at least one can prove existence theorems. They don't tell you much about what's going on, but if I have a square, well, these things are totally, I can certainly understand what they mean here and here. And so at least it looks like a framework in which one can define solutions for rough objects. We'll see that in more detail when I actually write down the definition. But yeah, the overall point is sets of measure 0, we don't care, it's measure theory.
Okay. Thank you.
Welcome.
And for the teaching, both are fine. I think both versions are, at least have advantages and are good to follow. So I would say what you feel more comfortable with is good.
Okay, great, thank you. Thanks for it's always nice. Okay, so if there are no more questions, then I will close the thing, and I'll see you guys before long. Yep, bye.
Bye, thank you.
You're welcome.